Good morning, dear students. In the previous class, we have completed that chapter nuclei. Today, we have to start new chapter, that is wave optics. It is very important chapter in optics. You know, there are two parts in optics, that is ray optics or geometrical optics. This is wave optics, also known as physical optics. So, it is one of the important chapter in JEE Mains point of view or advanced as well as NEET also. First of all, we have to see some introduction about this optics. You know, optics is nothing but the branch of physics which deals about light and its related phenomenon is known as optics. Light gurinchi మరియు దాని related phenomenon, the phenomenon exhibited by the light, we discuss in this branch of physics, that is known as optics. So, optics we can discuss under two headings, that is one is geometrical optics. Already you learned this chapter, and this is under another heading, wave optics. In geometrical optics you learned all the optical phenomenon like reflection, refraction, total internal reflection, images formed by the mirrors or lenses and optical instruments, prisms, all these phenomenon we discussed. So, all these phenomenon depends based on one property that is known as rectilinear property or rectilinear propagation of the light. So, in geometrical optics we explained all the phenomenon in this heading based on the rectilinear propagation of the light. That means light follows straight line path, that you remember. Whereas in wave optics, this is our chapter now, we discuss all the optical phenomenon like interference, diffraction and polarization. Discuss with these three phenomena in this chapter: interference, diffraction and polarization. So, these three phenomena based on wave nature of the light, means in wave optics wave nature of the light is considered, and based on wave nature of light we discuss these three types of concept. So, such heading is known as wave optics or physical optics. So, the branch of optics in which the optical phenomenon like interference, diffraction, polarization are described based on wave nature of the light is known as wave optics. Do you have the clear distinction between ray optics and wave optics? So, the branch of optics which deals the optical phenomenon like reflection, diffraction, total internal reflection, etc. based on rectilinear propagation of the light is known as geometrical optics. The branch of optics which deals about the phenomenon of light like interference, diffraction and polarization based on wave nature of the light is known as wave optics or physical optics. Is it clear? So, in wave optics we consider the wave nature of the light, right. Limitation between geometrical optics and wave optics. What is the limitation? See, when B is much greater than root L lambda or B square by L lambda is much greater than 1, then geometrical optics or ray optics is valid. Ray optics is valid, you remember. Here B means size of the interacting object, What is that? Like size of either lens or prism or mirror, etc. Size of the interacting. B is, that is size of the lambda, wavelength of light. L, distance between object and screen, remember, object and screen. So, remember, whenever the size of the interacting object is much greater than wavelength of the light, then rectilinear propagation of light is predominated, and based on the rectilinear propagation of light we discuss the phenomenon like reflection, refraction, total internal reflection, etc. Understood? So, geometrical optics or ray optics eppudu valid avutundi nana? When B is much greater than root L lambda, ledante squaring on both sides, bring this side, B square by L lambda much greater than 1, then ray optics or geometrical optics is valid. And the meaning enti? Size of the interacting object should be much greater than wavelength of the light. So, in ray optics or geometrical optics we use the optical elements like lenses or mirrors or prism, or that is, what is that? Images formed by the lenses or mirrors, etc. Here all size of the interacting object, lens of size of the lens is much greater than wavelength. Wavelength of the light, how much? Ordinary, that is generally visible light, from 3000 angstrom to where do you 7000 angstroms. What is the average wavelength? Roughly 4000 angstroms, average wavelength, 3500 or nearly 4000 angstrom. That means in angstrom means this is 4 into 10 power minus 7 meters, or 0.000, you can write it as in millimeters how much? 4 into 10 power minus 4 millimeters. The 0.0004 millimeters. This should be. And the size of the wavelength of the light is much. If the size of the object is this much or much greater than, generally what is the size of the lens or mirror? It may be about 2 millimeters or 4 millimeters, 2 centimeters, 4 centimeters like that, or 8 centimeters of diameter of the lens, which is far greater than, much greater than the wavelength of the light. That the light follows straight line path, light follows rectilinear path. Here the size of the objects or size of the lens or prism or mirror much greater than this value. This is very small value, 0.0004 millimeters, but it is centimeters only, 8 or 2, 4 centimeters like that, 10 centimeters. Such these are the size of the objects. This is much greater than wavelength of the light. Hence, wave nature of the light predominates. Then, whenever this condition fails, so whenever the above condition fails, then wave nature of light predominates. Remember, if this condition fails, ఈ condition fail అయింది అనుకో, అంటే దాని అర్థం ఏంటి? That is, if B is nearly equal to root L lambda or B much less than root L lambda, this condition fails means దీని కాంట్రరీ తీసుకోవాలి. ఇక్కడ B greater than L lambda ఉంది. ఇది కాదు అంటే either B equal to L lambda లేదంటే B should be less than root L lambda కావాలి. That means or B square by L lambda nearly equal to 1 or B square by L lambda much less than 1, then what will happen? Wave nature of the light predominates. So remember, ఎప్పుడు wave nature predominate అవుతుంటే size of the interacting object either equal to wavelength of light, nearly equal to the wavelength of light, లేదా wavelength of light కంటే చాలా తక్కువగా ఉంటే, then wave nature of the light considered, and based on wave nature of the light we discuss the phenomenon like interference, diffraction, polarization. Understood? And ఇక్కడ మనం తీసుకునేది అంటే size of the interacting object అంటే like pinholes, sharp thin edge. So these are the ఇక్కడ use చేసే interacting object. So what are the objects here? Pinhole, straight sharp edge or thin edge అంటాం. You say thin edge. So at these points whose size is comparable to the wavelength of light, then light follows that wave nature. Light exhibits wave nature. Based on wave nature we discuss that. Okay? So this condition important, they will ask. So what condition which facilitates us to use wave optics? So the condition which facilitates us to use wave optics or physical optics, B either equal to root L lambda or B much less than root L lambda. On squaring both sides you get like this. B square by L lambda should be either equal to 1 nearly or less than B square by L lambda much less than 1. Remember the terms have as usual meaning. ఏంటి ఇక టర్మ్స్ మీనింగ్ ఏంటన్నా? B అంటే size of the interacting object, అంటే ఇక్కడ size of the pinhole. L is distance between the object and screen. Lambda is the wavelength of light used. before we discuss about interference, we need to discuss some important terms which we are going to use in this chapter. That is, first one, wavefront. What is wavefront? ఈ టర్మ్ మనం ఫ్రీక్వెంట్గా యూజ్ చేస్తూ ఉంటాం ఇన్ ఫర్దర్ కమింగ్ టాపిక్స్. వేవ్ ఫ్రంట్ అంటే ఏంటి? ద లోకస్ ఆఫ్ ఆల్ ద particles of the medium which are in the same phase of vibration is called a wavefront. Listen to me carefully. The locus of all particles of the medium which are in the same phase of vibration. Say what it means. Suppose you know this is the source of light which sends disturbances in all directions through the given medium. If you take after suppose light is produced at t is equal to 0, 5 seconds all the disturbances reaches this point in all directions 3-dimensionally. So if you join all these particles which have these same disturbances, you get like a isophasal surface. Here the phase difference is same because all these disturbances have been started at the source 5 minutes back and they travel the same distance in forward direction d in all directions. So all these particles have same phase. ఈ పార్టికల్స్ అన్నిటికీ కూడా సేమ్ ఫేజ్ ఉంది. సో ఇలా సేమ్ ఫేజ్ ఉండే అన్ని పార్టికల్స్ని జాయిన్ చేసే ఒక సర్ఫేస్ని మనం వేవ్ ఫ్రంట్ అని చెప్పొచ్చు. వేవ్ ఫ్రంట్ ఈజ్ నథింగ్ బట్ సింప్లీ isophasal surface. What do you say? Isophasal surface. Isophasal means same phase. సేమ్ ఫేజ్ ఉన్న అన్ని పార్టికల్స్ని జాయిన్ చేసే ఒక సర్ఫేసే మనం వేవ్ ఫ్రంట్గా కన్సిడర్ చేస్తాము. సో లోకస్ ఆఫ్ ద ఆల్ పార్టికల్స్ ఆఫ్ ద మీడియం విచ్ ఆర్ ఇన్ ద same phase of vibration is known as a wave front. Here the phase difference between any 2 points on a wavefront is 0. Remember, phase difference between any 2 points on a wavefront. ఒక wavefront మీద ఏ 2 పాయింట్స్ తీసుకున్నా కూడా దాని phase difference అనేది 0 ఉంటుంది. ఇక్కడ 3 types of wavefronts we can define. They are number 1 spherical wavefront, cylindrical wavefront, and plane wavefront. So wavefronts ఎన్ని టైప్స్ ఉంటాయి నాన్న? 3 types. ఏంటండి? Spherical wavefront, cylindrical wavefront and plane wavefront. What is spherical wavefront? Spherical wavefront. It is produced by spherical wavefront. It is produced by a point source of light. Point source of light. Remember, spherical wavefront ever produce chestaru? Point source of light, like electric bulb. Okay, bulb తీసుకున్నారు అనుకోండి. This is point source of. It emits the light waves in all direction. Like this. Suppose source నుంచి 1 second లో light waves అన్ని ఇక్కడికి రీచ్ అయినాయి అనుకో. అప్పుడు ఆ 1 second లో రీచ్ అయిన డిస్టర్బెన్సెస్ జాయిన్ చేసే సర్ఫేస్ ఇది. దిస్ ఈజ్ కాల్డ్ అంటే ఒక స్పెరికల్ సర్ఫేస్ ఇమాజిన్ చేసుకో. దట్ స్పెరికల్ సర్ఫేస్ ఈజ్ నోన్ యాజ్ స్పెరికల్ వేవ్ఫ్రంట్. ఇమాజిన్ దట్ ఈజ్ వాలీబాల్ తీసుకోండి. వాలీబాల్ సెంటర్ ఆఫ్ ద వాలీబాల్ దగ్గర బల్బ్ ఉంది అనుకుందాం. ఒక 2 secondsలో అన్ని లైట్ వేవ్స్ సెంటర్ నుంచి సర్ఫేస్ ఆఫ్ వాలీబాల్ రీచ్ అయినాయి అనుకో. అండ్ అప్పుడు సర్ఫేస్ ఆఫ్ వాలీబాల్ మీద అన్ని పార్టికల్స్కి సేమ్ ఫేజ్ ఉంటాయి. సో దట్ ఈస్ నథింగ్ బట్ spherical wavefront. Surface of the volleyball is nothing but now considered as a spherical wave, like this. ఒక 5 seconds తీసుకున్నాం ఇంకా వేవ్స్ ఇంకా ముందుకు ట్రావెల్ చేస్తాయి డిస్టెన్స్. దిస్ ఈజ్ నథింగ్ బట్ సో దే ట్రావెల్ ప్యారలల్ టు ఈచ్ వన్ వేవ్ ఫ్రంట్. అలా ఎక్స్పాండ్ అవుతూ ఉంటుంది. రేడియస్ ఆఫ్ ద వేవ్ ఫ్రంట్ గ్రాడ్యువల్లీ ఇంక్రీజ్. దిస్ ఈజ్ నోన్ యాజ్ స్పెరికల్ వేవ్ ఫ్రంట్. Spherical wavefront. So, spherical wavefront ever produce chestana? It produced by point source of light. Example, a small bulb, point source of light meer teesukovachu, that produces spherical. Here one important point you remember, the light rays which are always perpendicular to the wavefront. వేవ్ ఫ్రంట్కి లైట్ రేస్కి మధ్య యాంగిల్ ఎంత ఉంటుంది అంటే 90 degrees. సో డైరెక్షన్ ఆఫ్ ప్రాపగేషన్ ఆఫ్ లైట్ అండ్ వేవ్ ఫ్రంట్ ఆల్వేస్ పర్పెండిక్యులర్. మీన్స్ డైరెక్షన్ ఆఫ్ ప్రాపగేషన్ ఆఫ్ లైట్ ఈజ్ నథింగ్ బట్ వేవ్ ఓన్లీ. దట్ ఈస్ నథింగ్ బట్ డైరెక్షన్ ఆఫ్ ప్రాపగేషన్ ఆఫ్ ఎనర్జీ. సో ద ప్రాపగేషన్ ఆఫ్ ఎనర్జీ ఈజ్ పర్పెండిక్యులర్ టు ద వేవ్ ఫ్రంట్. That you remember, a light rays perpendicular to the wave front. Clear? Now cylindrical wave front. Cylindrical wave front. A linear source of light, produces cylindrical wavefront. Which will produce linear source of light. Like oka tube light తీసుకున్నారు అనుకోండి for example, vertical. So the light rays which produced from all direction, if you take the light rays which produced from the linear source after same time ఒక 5 seconds తర్వాత ట్యూబ్ లైట్ నుండి ప్రొడ్యూస్ అయినాయి సేమ్ డిస్టెన్స్ ట్రావెల్ చేస్తాయి. వాటిని జాయిన్ చేసే సర్ఫేస్ తీసుకుంటే అవన్నీ కూడా ఒక సిలిండ్రికల్ సర్ఫేస్ దగ్గర ఉంటాయి. సో దిస్ టైప్ ఆఫ్ సర్ఫేస్ ఈజ్ నోన్ యాజ్ cylindrical wavefront. Cylindrical wavefront is nothing but a cylindrical surface that produced by a linear source of light. If you take any particle on this surface which has the same phase, the phase difference between any two particles on the cylindrical wavefront is again 0. The light rays are again perpendicular to this surface, radially outwards to the surface. So angle between the that is light ray direction and the wavefront is 90 degrees. Then plane wavefront. Plane wavefront. a distant source of light, a distant source of light produces plane wavefront. A plane wavefront produced by distant source, a distant source of light produces this one, means plane wavefront. If source is very long from the observation point, then the light rays which are coming almost parallel to each other. So, if you take sun is the source, then the light rays coming from the sun almost parallel to each other. Now, that wavefront produced by the parallel rays is known as a plane wavefront, like this. So, this is the plane wavefront. These are the light rays. So, light rays like this, coming like this. So, this is one plane wavefront. If you take a cylindrical wavefront, this is the source cylindrical wavefront. As time passes by, radius of the cylindrical wavefront gradually increasing. If you take a small portion on the cylindrical wavefront, it is almost a plane surface. Means when source is very large from this observation point. Now, a portion of cylindrical wavefront or spherical wavefront also becomes a plane wavefront. So, plane wavefront is produced by, this is plane wavefront. So, a plane wavefront is produced by the distant source of light. So, here 4 points you remember first. What is wavefront? Wavefront is nothing but isophasal surface, or if the locus of the all particles of the medium which are in the same phase of vibration is known as wavefront. 3 types of wavefront: spherical, cylindrical, plane. Spherical wavefront produced by the point source of light, cylindrical wavefront produced by the linear source of light, and plane wavefront produced by the distant source of light. So, understood that wavefront? Right. Now, we go through the next topic, that is Higgins principle. According to Higgins, what is states? Statement: every point on a wavefront behaves like a secondary source of light, and which emits secondary wavelets in forward direction. These secondary wavelets travels with the same speed of light in forward direction in the given medium. So, this point you remember. Higgins principle. Every point on a wavefront behaves like secondary source of light, not the original one, and each source of light emits secondary wavelets. These secondary wavelets travels in forward direction. Secondary wavelets travels in forward direction with the same speed in the given medium. Remember, say this is a source of light, imagine S, original source of light, small bulb. What happened? It emits light rays in this direction. These are the light rays coming in all directions. If you take, after 5 seconds, all the disturbances reaches this point. This is the original wavefront. We call primary wavefront. Wavefront produced by the original source of light. Which type of wavefront? It is a spherical wavefront. Point source of light produces spherical wavefront. Now, according to Higgins principle, every point on wavefront behaves like secondary source of light. ప్రతి పాయింట్ కూడా వేవ్ ఫ్రంట్ మీద ఎలా బిహేవ్ చేస్తుంది? ఇంకొక సోర్స్ ఆఫ్ లైట్, బట్ నాట్ ద యాక్చువల్ వన్, ఒరిజినల్ వన్. దట్స్ వై వి కాల్ సెకండరీ సోర్స్ ఆఫ్ లైట్ విచ్ ఎమిట్స్ సెకండరీ వేవ్లెట్స్. అంటే మళ్ళీ ఇది సోర్స్ ఆఫ్ లైట్ కూడా దాని నుంచి లైట్ వేవ్స్ ఎమిట్ అవుతాయి. సో దీస్ వి కాల్ వేవ్లెట్స్. సో దిస్ ఈజ్ అనదర్ సోర్స్ ఆఫ్ లైట్, లైక్ దిస్ ఇట్ ఈస్. So every point on a wavefront behaves like a secondary source of light which emits secondary wavelets. These secondary wavelets travel in forward direction with same speed of light. ఈ లైట్ రేస్ ఎంత స్పీడ్తో ప్రాపగేట్ అవుతాయో ఈ వేవ్లెట్స్ కూడా అంతే స్పీడ్తో ఫార్వర్డ్ డైరెక్షన్లో మూవ్ అవుతాయి. Now the forward envelope drawn to these secondary wavelets gives, దీనికి ఒక tangent drawn చేశాను అనుకోండి, tangent drawn to these secondary wavelets, the dashed line, you get another wavefront that is known as secondary wavefront. Secondary wavefront. What is secondary wavefront? The forward envelope drawn to the secondary wavelets is known as secondary wavefront. Means Higgins principle helps us to construct the new position of the wavefront. If you know the present position of the wavefront, present position ganaka teliste certain time tarvata new position of the wavefront ni manam construct chesukovachu. That is one of the important use of the Higgins principle. So Higgins principle em cheptundi, every point on a wavefront behaves like a secondary source of light and which emits secondary wavelets in forward direction. And one more point, these secondary wavelets travels in forward direction with the same speed of light in the given medium. The forward envelope drawn to the secondary wavelets gives secondary wavelets gives secondary wavefront. So if you know the present position of the wavefront, we can take the secondary position of the wavefront. We can discuss the secondary position of the wavefront. So this is about wavefront. Now Doppler's effect in light. So what is Doppler's effect in light. You studied already Doppler effect in sound, that is nothing but waves. Here we have to discuss in light also. So, you know, whenever there is a relative motion between the source of light and observer, then the apparent frequency or the wavelength received by the observer is not equal to the actual frequency or the wavelength. That apparent change is known as the Doppler's effect. So, when the source of light moving relative to the observer, then the frequency or the wavelength as received by the observer not equal to the actual frequency or wavelength of the source. That is, there is some difference between apparent frequency and the actual frequency. So, this phenomenon is called Doppler's effect in light, you remember. Remember, when source is moving either away from the observer, source of light here, or source of light is moving towards the observer, means when there is a relative motion between the source of light and observer, then the actual frequency received by the observer, the frequency received by the observer may not be equal to the frequency produced by the source. Means there is some difference between source of light, frequency of the source of light and frequency received by the observer. Such difference is known as apparent change. So, that apparent change in frequency received by the observer due to source of light and observer is known as the Doppler effect in light. So, here we discuss two concepts, that is blue shift and red shift. So, what is blue shift? When the source of light is approaching relatively the observer, then the apparent frequency increases and apparent wavelength apparent frequency increases and apparent wavelength decreases. In this case, listen carefully, in this case the wavelength corresponds to middle region of electromagnetic spectrum. EM means electromagnetic spectrum shifts towards what is that, blue end of the spectrum. This phenomenon is known as the blue shift. So, what is blue shift? It is very important point. When the source of light approaches relative to the observer, then the apparent frequency increases, and the apparent wavelength decreases. So, in this case the wavelength corresponds to the middle region of electromagnetic spectrum, shifts towards blue end. This phenomenon is known as the blue shift. Means if source is at source is moving related to the observer, what will happen? The distance between the source and observer decreases, means the frequency received by the observer increases. Frequency and wavelength are reciprocal, inversely proportional. So, wavelength increases. So, like that. So, the wavelength increases means, and frequency decreases. So, wavelength decreased means that wavelength corresponds to the middle region of the electromagnetic spectrum, shifts towards the blue end of the electromagnetic spectrum. In this case, apparent frequency f dash is equal f into root over 1 plus v by c by 1 minus v by c you take, or f dash is equal f of root over c plus v by, that is c minus v. Apparent frequency. Apparent wavelength lambda dash is equal to lambda of root into 1 minus v by c by 1 plus v by c, the apparent wavelength, or lambda dash is equal to lambda times root over c minus v by c plus v you take. So, these are the expression for apparent frequency and apparent wavelength. If these velocities are very small, when velocity of this is source of light much less than speed of light, then we can say f dash is equal to f of 1 plus v by c, that is nothing but, what do you say, f dash is equal, or simplify you can, this is f dash is equal to f of 1 plus v by c whole power 1 by 2 by 1 minus v by c whole power 1 by 2, and bringing upside 1 plus v by c whole power 1 by 2, 1 minus v by c whole power minus 1 by 2. So, f of 1 plus v by c 1 by 2 into 1 plus v by 2c you get from binomial expansion. So, this is also 1 by 2c. So, f of 1 plus v by 2c whole square you get it as f of 1 plus 2v by 2c, that means f dash is equal to f of 1 plus v by c. So, this is a expression for apparent frequency when velocity of the source of light is very small compared to the speed of the light. So, apparent frequency, that is f dash is greater than f. Similarly, lambda dash you write, lambda dash is equal to lambda of 1 minus v by c. So, lambda dash is less than lambda, apparent wavelength decreases. Then here redshift. What is redshift? When the source of light is moving relative to moving away relative to the observer, relative to the observer, then what will happen? The apparent frequency received by the observer increases and apparent wavelength that is apparent frequency decreases and apparent wavelength increases. So, in this case the wavelength corresponds to middle region of electromagnetic spectrum, shifts towards red end of the spectrum, shifts towards red end of the spectrum. This phenomenon is known as redshift. So, what is redshift? Jagrata vinandi. When the source of light relatively moving away from the observer, then distance between the observer and the source of light increases. That means apparent wavelength increased and apparent frequency decreases. Means the wavelength corresponds to the middle region of the electromagnetic spectrum, shifts towards red end. So, this phenomenon is known as the redshift. Here the formulas we can say like this: apparent frequency f dash is equal to f of 1 minus v by c by 1 plus v by c, this whole root, or f dash is equal to f of c minus v by c plus v. Our wavelength is equal lambda of root 1 plus v by c by 1 minus v by c, you see. Clear? So, this is for smaller velocities, that is when v is much less than c, frequency f dash is equal to f of 1 minus c by, that is v by c, and lambda dash is equal lambda of 1 plus v by c. So, here the fractional change in wavelength, it is important, delta lambda by lambda is equal plus or minus v by c, fractional change in wavelength. In case of redshift, for redshift you get delta lambda is equal plus v by c into lambda. Percent of change also you can calculate. This is for blue shift, you get change in wavelength delta lambda minus v by c into lambda, you get. Here lambda, delta lambda is final wavelength minus initial wavelength. It is about blue shift. So, these two are the important formulas: fractional change in wavelength for blue shift and red shift. Frequencies are reverse. The fractional change in frequency you get delta nu by nu is equal plus or minus again v by c. For blue shift it is, you get delta nu is equal to minus v by c, blue shift means plus into nu. For red shift you get delta nu is equal to minus v by c into nu. It is about this red shift. These two remember. So, one more important thing, that is Doppler effect in case of sound is asymmetric, whereas the Doppler effect in case of light is symmetric. So, it is about this Doppler effect in light. So, understood what we discussed the concepts here. Today we discussed about first the limitation between ray optics and wave optics. So, whenever the size of the interacting object is either equal to wavelength of light or less than the wavelength of light, wave nature of the light predominates, and based on the wave nature of light we discuss interference, diffraction and polarization phenomenon. Later we discussed wavefront. So, the locus of all points of the medium. which are in the same phase of vibration is known as wavefront. Three types of wavefront exist: spherical wavefront, cylindrical and plane wavefront. So, a point source of light produces, that is spherical wavefront, linear source of light produces cylindrical wavefront, and distant source of light produces plane wavefront. Here Doppler effect also we have to discuss, that is the apparent change in frequency of source of light due to relative motion between the observer and source of light, then actual frequency received by the observer may not be equal to the actual apparent frequency may not be equal to actual frequency. Such relative motion when exists between the source of light and observer, there exists two type of phenomena, blue shift and red shift. When source is relatively moving towards the observer, blue shift, and when source is moving relatively away from the observer, red shift occurs. So, these are the relative formulas for the red shift and blue shift. So, that is all for today's class right now.